Good evening. It is evening. It's getting dark out there. So who knows? I may be too tired to do this. Maybe this lecture will be incoherent, but we'll see. The last recording that I made, or last set of recordings that I made, was on capacitance. And so I talked about having a couple of conductors, which I referred to in that context as plates. And although it isn't necessary in theory as a practical matter, the two conducting plates are typically identical in both what they're made of and in their geometry, their size and shapes, dimensions, and so on. And so I talked about it, and I said, okay, well, you hook them up, and you set up some sort of potential difference, and so charge goes from the one plate to the other plate and sets up another potential difference. And then the question was, how much charge can we store in the capacitor? And it turned out that the amount of charge we could store in the capacitor depended on how big a potential difference you established across the, between the two capacitor plates, and so on. And then it also depended on the capacitance of the arrangement of those two conductors. Remember, capacitance was a physical constant that involved, as I said, and the geometry of the plates. And that was all well and good, and so I went through all that, and it was very exciting, very interesting, and you couldn't wait for the next recording because it was so exciting. I want to point out, though, that in that discussion, I snuck something past you, and I didn't make an issue out of it, but I want to make an issue out of it now. And that was, so you remember the situation. I had a couple of conducting plates, and in this case, I'll make them rectangular just because that's easy to draw. And so a metal plate, and then another metal plate nearby it. And then I said, okay, let's connect a battery or a power supply or something that we will represent with this peculiar symbol. That's a sequence of 4 parallel lines, too long, too short. And this, as I'll describe in a future lecture, actually is the electrical schematic symbol of a battery. Very possibly you already knew that. So we set up this potential difference, and I said, and so then charge flows from the one plate to the bottom plate. It flows from a high potential to a low potential. So positive charges, I said, flow. And there it was. I said it twice just now. The thing that I just blew past in the capacitance lecture, I don't want to blow past it now. What I said was that charge flows from the top plate to the bottom plate. This is a first. Up until I mentioned capacitance, we've never had our source charge flowing. It is a source charge here. I'm moving charge from the one plate to the other plate. That establishes a potential difference between the two plates. That establishes an electric field. The electric field is always created by a source charge. So we are, for the first time, allowing our source charge to move. Up to now, we've been studying only electrostatics, which implies, its very name implies, that the source charge is static, is motionless. But now we've relaxed that restriction, and I told you at the beginning of the quarter that I would do that. And this is the time, okay? And now what we have to do is we have to start exploring what consequences there are of allowing the source charges to move. And that's what this sequence of lectures is about. What we're going to discover is that once we allow the charge to move, an entirely new phenomenon that we have not seen before and could not have seen before, this new phenomenon will suddenly appear. So, although I could use the diagram that I'm currently erasing, I don't want to. Let me do it with a slightly different situation. Something fairly familiar, perhaps. And so let's suppose I set up the following physical situation. Let's see how much room I have to work with here. Okay. I'm going to presume that you know what a battery is, but if you don't know what a battery is, sorry, I'm just getting my bearings here. Seeing how much space I have on the recording. You probably have a pretty good idea of what a battery is. The interior of a battery and what makes a battery work is a subject for another day. But for now, all you need to know and care about is that a battery is a source of potential difference, which creates an electric field from source charges. And if you expose test charges to that electric field, those test charges will experience a force. And now I'm going to allow, well, anyway, so let me just start that. So I'm going to, just for convenience, I'm going to draw my battery like this. There are not many batteries that look like this, but there are some. And so let me do this. Okay, so there are some batteries that are built like this. What's going on inside a battery we don't need to care about, but suffice to say that, as always, well, so the battery is going to be a source of electric potential difference, which I will label V, okay? And the potential difference, as always, is a difference between the potential at one place and the potential at another place, and one of those places is typically defined to be potential energy 0. Usually, on a battery, one end of the battery is defined to be, in fact, always, as far as I know, one side of the battery is defined to be potential 0, the other side of the battery is defined to be potential whatever. For a regular D-cell battery, it would be 1.5 volts. Potential from measured from the bottom of the battery. There's 6-volt batteries, there's 9-volt batteries, there's 12-volt batteries, and so on. So whatever the difference is. Now, I'm going to tell you something that will not come as a surprise to you. If I were to connect a wire here, and then right in here somewhere stick a light bulb. And the only reason for the light bulb is so that we know that something is happening. And what is that something? Well, what will happen is, I'm sorry, one second here. Click. Okay, what will happen is, for reasons very similar to what I described in a capacitor, charge is going to flow. Specifically, charge is going to flow from the high side of the battery, the high potential side of the battery, to the low potential side. And so if we decide that, for example, this side here is, I don't know, I'm going to make it over 12 volts, and then this side over here is defined to be 0 volts, then just like in the capacitor, charge in this battery will flow from the region of high potential to the region of low potential. The wire that we've attached to both sides of the battery is a conductor. And a conductor, as we've talked about before, means that charge can flow freely in it and through it. Okay? The only reason I put the light bulb in there is so that we know when the current, well, and that's the word, we know when electric current, that is, sorry, let me start that over. We know when an electric current is flowing. In other words, we know an electric current is simply a flow of charge. I'm going to actually define electric current in a formal sense in a while. Anyway, we attach this, charge flows from the high potential to the low potential, and rather than drawing a bunch of plus signs, it flows through the filament of the light bulb or through the LED or whatever it is, and it flows down like this. The concept, and I've already said the word, so let me formalize it. The concept of charge moving is represented with the word, or the phrase electric current, or usually just current. And so the word current means flow of charge. And just like a water current is a flow of water, okay? Or flow of water molecules, if you insist. So in this case, the current, as I say, is going to flow like this. And there's nothing terribly remarkable about that except that something else is going to happen that I haven't described yet, and that is this. It is an experimental observation that when this situation happens, not only does the light bulb light, frankly, the light bulb is irrelevant to the conversation, or at least irrelevant to my current purposes. Again, I only put it there so that the bulb lights up, we know that there's a current flowing. Okay. Now, the new thing that happens that we have not seen before is that when this current flows, these two wires well, I guess I'll just do this. The two wires repel each other. Okay, so that the wires actually end up bowing outward. Okay, so in reality, what you end up seeing is hopefully a better pen than that one. What actually happens is that I guess I'll start making a new drawing. Wire bows out slightly. Our light bulb is there. The two wires, in short, repel each other. Well, that's not terribly surprising, of course, because after all, we have charge flowing through these wires. The charges are all of the same sign, and so you think, oh, well, of course, they repel each other because, Coulomb repulsion, right? QQ over R squared. And that's all well and good, and so we have current flowing like so. Okay, but I don't want you to miss the significance. The two wires repel each other. That means that there's a force acting on each of them, and that's what these light brown arrows are. These are force vectors. Okay, and so the explanation seems clear. The Coulomb repulsion causes them to push away from each other. Unfortunately, or actually, for those of you who like puzzles, this explanation, while perfectly sensible, turns out to be flatly incorrect. And we can see that that's incorrect by running a variation on this experiment, which goes like this. And I'll try to draw this. A little bit tricky here. Okay, so again, we take our battery and a wire and our light bulb and so on. So 12 volts here, 0 volts over here. Okay. And I'll send my wire up, light bulb, work down, and then, make sure you get this right. Better. Okay, and there's our light bulb. In this situation, wired up in this peculiar way, highly artificial, its only purpose is to show something. The current then will again flow from high potential to low potential. So it will flow from here, up here through the light bulb. So it's pointing that direction, here it's pointing this way. down here, it's pointing that way, goes through here, pointing upward, sideways that way, over here like this, down like this, through that loop. And so this little looping bit is to indicate that there's not a physical electrical connection right here. This loop here jumps over the wire underneath it, as it were, and so flows like that. Okay, the key thing that I want to draw your attention to is that unlike the previous example, which let me draw your attention to it here. In the previous example, the flowing charge, the current, is flowing up this direction and down this direction, whereas in our new situation over here, you'll notice that these two wires, the current is flowing in the same direction, so they're parallel. In the previous one over there, the currents are flowing what I would say anti-parallel, where here they are flowing parallel. And the reason I mention all this is what we find here. Actually, I'm going just for the sake of my own drawing needs, I'm going to alter this just slightly. All I'm going to do is put the two wires a little bit further apart. Current up like this. Okay. What we find in this case is exactly the opposite of the previous situation. We find that these two wires, when we run the current, they actually attract each other. And of course, unsurprisingly, they are equal in magnitude and opposite in direction, Newton's third law, of course. This, I hope it is obvious to you, cannot possibly be explained by the electric force, by the Coulomb force, because that's still the same sign of charge. So they should still be repulsive, but they are manifestly not. These two wires very noticeably, I mean, it's not a large effect, but it's a noticeable effect. They actually do bow toward each other. They attract each other. So clearly, whatever force is causing this attraction here, it absolutely is not the electric force. And by extension, therefore, we have to assume that the repulsion that we saw in the first example isn't the electric force either. Okay? And it turns out that that's true. There is another force at work. And so it is that other force that we want to investigate. And so, so we investigate that. So in short, if two currents now, not just charges, but if two currents, moving charges, if they are flowing parallel to, well, if they're flowing in the same direction, then there is a force of attraction between those two currents, whereas if the two forces are flowing opposite each other, I can't do it with my hands, flowing opposite each other, there's a force of repulsion between the two currents, and therefore between the two wires that carry the current. So that's the new force that we want to investigate. So it was investigated, and there was one other effect that was noticed. You are perhaps familiar with this device here. This is a compass, a magnetic compass. Its purpose is to find the North Pole. But the fact is that compasses don't know anything about the North Pole. All they do is respond to magnetic fields, whatever magnetic fields happen to be around. Okay, and in this particular case, the North Pole happens to be one of the strongest fields that it experiences, but I can certainly give it a stronger one. Over here where you can see it. There we go. All right, so the point being that this device responds to magnetic fields. This is a permanent magnet here that I have. Do you have anything? Oh, yeah, there we are. Permanent magnet. Okay. All right. Well, the reason I bring this up is because another thing that was discovered in the course of experimenting with electric currents, and this force of attraction or repulsion, as the case may be, was that when the electric current is flowing, along with these wires repelling or attracting each other, depending on the direction of the current flow, in addition, we found, it was discovered experimentally and accidentally too, that compasses were affected when they were brought near wires that were carrying electric currents. So now we have a new piece of information about this force. Along with this behavior of sometimes repulsive, sometimes attractive, we also noticed that it affected magnetic compasses, but they, the physicists back then, and back then I'm talking about the early to mid 1800s. Compasses were well known, and people knew what they did, and they didn't really know how they did them, but they certainly knew what they did. They acted and reacted to magnetic forces, permanent magnets, the North Pole, and so on. Okay? But no one had ever associated compasses with electric currents. It was permanent magnets in the North Pole. No one ever thought about electricity. As I think I mentioned in one of the earliest lectures for this course, in the early days of all of this stuff, electricity as a phenomenon and magnetism as a phenomenon were considered to be two completely different, two completely independent fields of study. This was one of the first hints that, in fact, electricity and magnetism are not so independent, that they do interact or interfere or interrelate with each other. Okay. Finally, more than that, once it was discovered that a compass was affected by a current, then the question is, what are the details of that? And the answer to that is complicated and not particularly drawable, but I will do a little hand waving anyway. And so one experiment was done that arranged to have a current flowing through this wire. And I'm getting ahead of myself here, but I need to write something. So the symbol for an electric current is the letter I. Depending on your book and depending on your teacher, the symbol for the electric current will either be lowercase I or capital I. My personal preference is to use capital I. I believe your textbook, or at least the textbook that people were using at the time I made this recording, which could have been 20 years ago. I have no idea. I could be dead now. All right. Anyway, many textbooks will use lowercase I. I don't like using that because it's too easy to confuse it with the square root of -1. But anyway, so capital I for electric current, and I will define electric current formally in a later lecture. Anyway, so we bring the compass needle here near it, and then we ask the question, okay, what happens to the compass needle? What's the effect? In more physics-y language, the question is, what force does the compass needle experience? Okay, and the answer turned out to be, you think, well, what are the possibilities? Either the compass needle is going to be attracted to the needle, so the compass needle will point toward the needle, or I'm sorry, back up. Compass needle has two ends. We call them the North Pole and the South Pole of the magnet, and we call them those because they were originally designed to point towards the North Pole and the South Pole of the Earth. And so we sort of imagined that since the electric current seems to be the source of some sort of, what do we have to call it, a magnetic force, I guess, that the compass needle, one end of the compass needle, either the North Pole or the South Pole, but one of the ends of the compass needle would point either directly toward the wire, or it would point directly away from the wire. And neither of those turned out to be the case. In fact, what we found is that the North Pole, South Pole points in a direction, in this example, if I held the compass like this, the North Pole would not point towards the wire, it would not point away from the wire, but rather, in this case, it would point into the board. Wait, see, is that right? Let's see. Yeah, I think that's right. So direction of the force would point like this when you're over here. But if I brought the compass needle over on the other side, here's the really peculiar part. If I brought the compass on the other side, then we found experimentally that the force on the compass needle would point out of the board. Okay. So this is all, and if I, on the other hand, brought the compass needle out in front, what we would find is the North Pole, South Pole would point that way. And if I were able to get the compass needle behind the board, as you probably already guessed, it would point, the compass needle would point that away, okay? So, in short, what we find is, by the way, I should warn you, this analysis is slightly misleading and I'll have to correct it, do a little better job later. What I've actually drawn here is not the force on the compass needle, but it's related to the force, so close enough. The point that I am trying to make is that the effect of this new phenomenon is that it causes the compass needle to never points towards the wire or away from the wire, but rather it points in, sort of perpendicular to the wire everywhere. And what actually happens is that if I have a wire that I'm holding up, if I can do this like this, if I move the compass needle around the wire, what happens is the compass needle spins as I spin the wire, and the compass needle never, in its motion, the compass needle never points toward or directly toward or directly away from the wire. It simply, it does this. Get a red pen, easier to see. Compass needle, as I move the compass around, the compass needle itself spins around in the sense that I'm sort of trying to describe here. Okay. Okay, probably that's enough. So this is very peculiar behavior, and we're going to need a little more thought to come up with a mathematical expression that will produce this effect. As I say, this drawing I've made has a small but important error in it. I will correct that in the next recording when we actually figure out what's going on with this force, what's causing the force, and what the mathematical relationships are.